everyone, this is Sean Mullery from Electronic Engineering at IT Sligo, and in tonight's multi-view geometry and computer vision class we're going to be looking at finding shapes. We're going to be sticking to some fairly simple shapes in this particular example for tonight, and this is a reasonably short set of slides, so it shouldn't be too taxing on you. But I don't want you to get the impression that just because it's a short number of slides that you don't have a lot of important information in here. There's some very, very important concepts here which get used again and again and again throughout computer vision. So, don't judge it based on the shortness of the slides. The other thing to mention is that we're really only going to look at lines here, but this can be extended to almost any shape that can be given a mathematical model. And indeed, for some of them, it can be extended to arbitrary shapes. But as with any of the things that we do in computer vision, we don't want to go down absolutely every avenue. We need to try and kind of keep it to some reasonable amount, and so that's what we'll be looking at tonight, just at lines. But just be aware that you can extend these to much more significant shapes as well. So many computer vision applications require us to look for specific shapes. So examples of this would be, you might be looking for lines or circles or squares, etc. And to kind of keep in mind with regard to this, that all you're looking at is brightness values within an image. So when we see something, when the human eye sees something like a line there, the computer just sees numbers. And so we need to have some mechanism whereby we can actually turn that into the concept of a line or a circle or a triangle or any sort of other shape for that matter. So there's always that jump that has to be made. So firstly, we need to be able to decide that a pixel value is either part of some greater object or not. And then when it is, how do we decide what that greater object is, and how do we maybe make a mathematical model of that object as to what it is? So if it's something like a line, how do we come up with the mathematical model for that line so that we then have some interpretation of where that is? Okay, so all these things are important, and each different thing is a step along the way in order to try and get to that. So if you consider the front-facing camera on a vehicle, we may want to detect lane markings, which are straight lines. But again, they're straight lines and they're going to be in a particular orientation. So we're going to be, it won't be good enough to just find the lines. We want to find out the orientation that they're in and where they're going, if there's any curves in it and so on. We might be looking for road signs, and road signs come in different shapes and sizes, but generally they're these strict mathematical geometric shapes. So you're looking for circles, you're looking for squares and triangles and so on. And in doing that, once you find a particular type of shape, that you've narrowed it down to a subset of particular road signs that you might be expecting. So, for example, if you know within a particular jurisdiction that circular signs will relate maybe to speed only, let's say. Now, I know that's not necessarily the case, but let's imagine that that's the case. You now have a smaller set to search from when you want to determine what speed is it at. So you're going to be looking for text within that once you've determined that you've seen a circular shape and it's a very clear geometric shape. So, you'll be covering in other subjects like applied statistics and probability. What's the probability that what you've seen is a road sign, first of all? And then within that, if you've determined that it's a road sign and that it's a circular shape, you're now not looking over the entire distribution of possible road signs. You've now limited to the particular types of road signs that you're expecting. And with other information, you may be able to narrow that down so that rather than you just relying on being able to read the text of it, which could be obscured for all sorts of reasons, you might have all sorts of other information that would be helpful. So, for example, you'll normally be aware that if you're slowing down in a car, if you've gone from a 100 kilometer zone down to a 60 kilometer zone, and then you reach another one, it's likely that you could be, you're going to be looking for maybe a 50 kilometer zone that you're continuing to slow down the speed, particularly if you're entering an area that the GPS says is an urban area. And so you might be expecting that the next sign is going to be a 50 kilometer sign. And really what you're looking for is, well, where is that positioned, so that you can then decide to slow down to that speed at that point. So you'll be taking information from all sorts of different sources and trying to use it together. And this is why being able to find shapes is so important, because the shape will actually tell you an awful lot of the information. It could be traffic lights you're looking at, and you'll know the general shape of a traffic light. It'll be a rectangular shape, but there might be little parts protruding out from it depending on what angle that you're seeing it from. And of course, the lights themselves will generally be circular. But of course, you're well aware that there are many traffic lights that will have an arrow associated with them. So you might be looking for that arrow as a shape and maybe some sort of mathematical model of that instead in order to be able to try and tell what it is you're supposed to be doing. And of course, then you're trying to figure out, well, which of those lights is associated with where I'm going and so on. Okay. So what we're going to do is we're going to start with the idea of a line. That's no problem, Niall, not at all. So we're going to start with the idea of a line, and we're going to take that as the basis for what we're looking at. But do remember that we can really extend this to almost anything that has a mathematical model associated with it. So imagine we have a number of points, and we wish to determine the best straight line that would fit all those points. Okay. So for example, let's imagine that we've got a load of points. Okay. Now you can all probably see there that it makes sense that we've probably got a line going through the center there. It's not necessarily, it's touching some of them, but not all of them. And it would be ideal if all of these points were definitely on a line, but that won't always be the case. Now the reasons that it might not be the case can be quite varied. There could be distortions in the lens of the camera. It could be, a broken, something's happened to me there, guys. My system is gone. Just give me 1 second. Now we're back up and going. Sorry about that. Somebody went blind there for a second. This could be something like a lane marking of that, and the lane marking could be all broken into bits, and you've only got these little bits of dots and so on. It could be that just simply the brightness that's coming back off these things is brighter in some places than others, and when we do some form of thresholding to try and decide what's a point and what is not a point, that we run into the problem of not being entirely certain, or not having these perfect dots along a line. And so what we might want to do is to fit a line to those. So how many of you have, in some point in the past, maybe more recently, or maybe a long time in the past, have done something like fitting a line to some points? Have any of you done that as an exercise in the past? Yeah. So some of you might have done it maybe just in Excel or something like that with some data, and you're trying to do it. Oh, you did it with Leo last year. Or last semester. That's good. And we'll actually be re-looking at some of the maths of that. So I'm glad to hear that you'll be familiar with it. So did you do that as part of your linear algebra subject, Maurice? A least squares idea. Oh, regression. Okay, very good, very good. Touched on it. Okay, well, that's no problem. We'll be seeing it a little bit again here, and then I'll be looking at some other possibilities for it. But just so that you're aware of it, that's great to know. Okay, so imagine we have a number of points, and we wish to determine the best straight line to fit to these points. There may be a perfect answer, but normally there will be some discrepancy, and we'll have to find the best fit. And that's what we come across more often than not, rather than this situation where mathematically, and you'd be aware of the mathematical definitions of these things. If your y equals mx plus c, if that works out for a particular value of x and a particular value of y, if that formula works out, then you know that you're sitting on that line, and there are lots of other things that you can do in order to try and figure out if you're sitting on a particular line. And that assumes that we've got this perfect mathematical model and we're trying to fit these perfect lines. But if we don't have that, we have to find all the different ways of fitting it. So one area is one system to use is a thing called least squares fit. And the idea here is that if we take our example from previously, this one here, which I'll just move on to here so that we have it here beside us. What we really have is a situation whereby we have little gaps here in what we're doing. So we've got a gap from there to there, okay, and we've got a gap from here to here. So there's a gap on the bottom side and another gap here. These ones are a little bit off it. And what we can do is we can measure those gaps And what we want to do is we want to find a line. So we want to be able to take our line here. And what I can do with my line is I can start moving it all to all sorts of different places here. And by calculating the gap between each of the different points and getting the square of those, that's where the square in least squares fit comes from. Getting the square of those, what we can do is we can try and determine, well, what is the best line that's going to fit that. So the smallest number when we total all of these things up is what will give us the best number. So we have a formula for the line, which is just your y equals mx plus c, and we can just call that basically a function of x and m and c. In other words, we put in a different value of x, we put in different values of m and c, and we try and figure out, well, which one of them gives us the value that's closest to all the different y's that we have. And what we do is we get the square of that. Now, why do we get the square of it? Well, there's a number. Firstly, it makes things a little bit simpler for us in one way, because in certain cases we can be below the value, and in certain cases we can be above it. So therefore, we're going to end up with situations. We're getting the values of our points here, and we're seeing how far are they from the line. And what we then do is we get the square of those. And as I say, with the square, it solves one problem, which is that any negative values become positive by squaring them, and the positive values stay positive. So we get the total error that's there. Okay, so that's the first problem that it solves. But the second problem that it's whether it's a problem that it solves or whether it's a problem that it causes really depends on the situation. But what we do is we really penalize badly any values that are a long way away from the rest of the values. So in this particular case, the one I've shown here, if it's a long way away from the rest of them, in other words, an outlier, then it will have a very large effect. And if we try and minimize this, what will happen is our line here will get drawn more towards it. Okay, so it'll get dragged a little bit up further towards this because it wants to minimize that. And all the other smaller errors, even when they're squared, will become less significant than this big one when it's squared. Because, of course, as soon as we square a number, we have an issue. Okay. Part of the reason that people use these squares, though, as well, is that it makes some of the other maths a little bit simpler. So let's say, for example, if I have x squared, if I get the derivative of that, of x squared, what value do I get, or what would I get from that? So get my dy dx of this. Dy dx of that. This is not a trick question. Okay, good. It's 2x. Okay. Now the thing is, if I just have x on its own and I get a dy dx of that, what's dy dx of just x? Yeah, it's just 1, which doesn't tell us a whole lot. Okay, because it's just a constant. Now, one of the things is that when we want to minimize something, does anyone know what the mechanism for what's the general mathematical mechanism for trying to find the minimum of some function? Do you know what the strategy is? It's actually not integrated. It's another one. Yeah, no, that can give you a certain amount of information, but actually the normal way is get the dy dx or get the derivative of it just once, and then set that equal to 0 and work it out from there. So you then find out what value, and the reason for that is if we have some sort of a function, let's say it's like that, and I want to find out where's the minimum, then what I'm going to be looking for is where is my derivative equal to 0. In other words, where is it straight along the bottom? And as Olivia said, the slope is equal to 0. So where's my derivative equal to 0? Okay. So this means that, or where the change is 0. Now, of course, we could have a maximum at that point as well. So it really depends on the conditioning of your particular curve and so on. But that's a mechanism that a lot of people would use, and therefore having the square in there usually makes things actually a little bit easier, because we can get that and we still got our x value in there. Whereas if you do it the other way, you're just left with a 1 there, or a constant, and things don't work out quite as easily, and you normally have to do a little bit more work. Now that said, That's not the way we're going to go about it, okay? So we have it written there in the last sentence. To find the minimum, we take the derivative with respect to m and c, and we set it to 0. That's, by the way, just in case I've never told you that, normally when I ask a question, the answer is actually written on the slide. I just have forgotten that it's written on the slide, and normally the students forget to look at it as well, which is works out great in the end. What we're going to do is we're going to use a linear algebra mechanism for doing the least squares fit, and you can do it like this. You can basically get a load of your y values here. No, I think you've lost me there. Have you got me back there, guys? Can you hear me? Yeah. So the system seems determined to test me tonight anyway. We shall try to remain calm. Okay, so I think we just got onto this slide here, had we, the least squared fit here, linear algebra thing. We'd gone from there to there, yes? Yeah. Okay. Yeah. Okay, so we're going to use a linear algebra mechanism called the least squares fit. And what we do with this is we take each of our y values here, and we take each of our functions. Now the function is just y equals mx plus c, but of course we've got y1 equals mx1 plus c, y2 equals mx2 plus c, and so on. And what we're trying to find is what is the value of c, or what is the value of m and c that's going to try and match each of these the best. Okay, it won't match them all perfectly, but match them the best. So the mechanism for doing that is we can set this up as basically as in matrices. So we have our x1 and our 1 there, and if you notice, if you do this multiplication, you get so maybe just undo that, x1 multiplied by m, which is what we have up here, and then 1 multiplied by c, which is what we have there, and the two add together, and that gives us our result, and that equals our y1 here. Okay, in each case. Maybe just delete some of that off the slide. Okay, and we can write that as we can call this entire vector here, we can call that B. We can call this matrix here, we'll call that A, and we can call this vector here, we'll call that D. Okay. Now, what we do in this particular case is we've got B is equal to AD. And what I'm going to do is I'm going to multiply on the left-hand side of both of them, I'm going to multiply by A transpose. Okay, so in other words, basically the transpose of this matrix in the middle. So I have an A transpose there and an A transpose there. Okay. Now what I can then do is I can multiply both sides by A transpose A, which, well, we'll talk about that matrix in a second, right? But we'll get the A inverse of that, and we'll take A transpose A and get the inverse of that. Okay. Now, you should notice at that point then that inverse is going to cancel out against this. So A transpose A and A transpose A inverse cancels out against each other, and that leaves us with just the D. So what that tells us is that if we get this A transpose A, get the inverse of it, multiply that by A transpose B, we will find out the value for D. Okay. Now that A transpose A there, if you actually think about it, this is this is going to be an N by 2. Okay. And the A transpose then is going to be a 2 by N. So you've a 2 by N by 2 is what we have. So we have a square matrix in that case, because we're going to end up with it basically a 2 by 2. Okay, and of course 2 by 2 is going to suit us, because it's going to work out with the rest of it as well, and we can get the inverses and so on at that. So once it's a square matrix, we can go and get an inverse of it and so on. So this is useful. One thing to be aware of is that it looks like we're creating some sort of magic here, because we said that all of these points, a little bit like the example right back here, did not necessarily fit the line. And yet now somehow we found a solution. And this is an unusual solution because what we have is we've got n equations, but only 2 unknowns. And because each of the equations, none of them perfectly match the unknowns, or they don't perfectly match the same set of unknowns, it's unusual that we get this to work at all, okay, because we've got so much noise in it. But what is important to remember is that what we're really doing when we do these sort of calculations here is that we are projecting this idea in matrices and vectors of projecting onto something. And what we're effectively doing is we are projecting on to the best line. Okay. Now, when you project onto something, you lose any of the vector that's orthogonal to that, that's at 90 degrees to that, and you only take the section. So let's say, for example, if I have 2 vectors, so I've a vector there, and I take, let's say, a blue vector here, it's up in that direction. The only part that is projected onto the red one here is just that section there. So just that part of it there is the bit that we keep. And we have lost all of this part here. And that is effectively what's happening is we are actually losing information with what we're doing here by coming up with a best fit line that fits this particular, that fits all of these points in its best manner. So this is not by any means an absolutely true solution or otherwise. It is a best fit in the same way as the other minimum one was, how can we get this to a minimum level? It works exactly the same as the least squares idea, okay? And you can kind of see where the least squares idea comes in because you're multiplying an A transpose by an A, so you're kind of multiplying these points by each other, so there is a squaring going on there. So you can kind of see how that is actually coming out of it, even if you don't have a full intuition for it. Did you do any of that that idea? Have you seen this idea A transpose A inverse by A transpose? Have you seen some of that in last semester's you did? Okay, that's great. So now you're seeing the actual use of it, and actually SVD Daniel will be coming up a little bit later as well, and we'll be I actually mentioned I think in the next lecture. So I'm glad to see that you covered that as well. And we see more of it throughout the course. Is a very important concept as well. So the least squares idea is where we have an over constraint, basically where we have more points and more equations than the unknowns. So we have n equations, but we only have 2 unknowns, for example, in this case. And of course, this could also be the case for any other sort of geometrical shape that we could basically write an equation for. So, you know, we could come up with some sort of quadratic equation or something like that, or maybe a sine wave or something, and we're trying to find something that's going to fit it, okay? So least squares is generally an over-constraint problem, i.e. many more equations than unknowns. You might think that that's always a good thing, but because of noise, we can find that some of those points, well, none of the points always fit perfectly with each other, and secondly, the situation of having a very large outlier can screw up everything else on us, because it can give it can have a much larger effect than the rest of the points, even though it's clearly the one that should have very little effect on them. So it's not ideal in all situations. Consider the problem of outliers. The error on an outlying point is much larger than the other points, and given that it will be squared, then the outlier has a very significant impact. If we try to minimize including it, by including it, then we face a line that is probably well away from where it should be. And we saw the example of that. The second problem is that of assignment. So in an image with multiple lines, how do we know which points should be assigned to which lines before fitting? So imagine the example I have here where I've got my points there as I've already drawn. And I've got some other points here. And they're heading up generally in this direction. Now, the human eye is pretty good at saying, I reckon there's another line up here. I reckon there's another line that's in that direction there. But the computer has no such sense for that. So what it might do is if we had no way of separating these points from each other and saying, you know, for example, that, well, all of these points here, they should be blue, let's say, for example. Okay, so all those points are blue and these ones are red, and now I have some way of telling them apart. I know which ones are which. But unless we have a mechanism to actually do that, and that requires you know, the computer to have some sort of a knowledge that it may not have. So otherwise, what it will do is it'll take all those points as being the same. It'll try and maybe do a least squares fit, and what it'll do is it'll maybe take, and I'll just draw this as a black line here. It'll take a line that's kind of the best fit of all of them together, which is somewhere up in that direction there, which, as you can see, is neither good for one or the other. So it doesn't really help us. So that's something to be aware of with least squares, that unless you know what points to assign to what lines, you run into a bit of a problem. Now, this brings me on to an idea, or an algorithm called RANSAC, and I have one slide on this, and then I'm going to show you some drawings. But this is a really important algorithm in computer vision. So again, as I say, just because there's just one slide here, maybe describing it, I don't want you to get the impression of its lack of importance. Maurice, I don't know if you remember at the conference you went to there in Belfast. There was a keynote guy on, I think it was on the second day. He actually asked this question at the very beginning for people to put up their hands as to who knew this algorithm. I don't know if you probably remember the incident more than that, but this is actually the algorithm that he's referring to here, and it is very important in terms of computer vision and its usage. It gets used all over the place. So I don't know whether you remember that or not, but in any case, so. Random assignment and consensus is what this stands for, and this solves the outlier problem. So what we basically want to do here is we want to have some sense, and we make this decision ourselves basically based on the data, but what we would say is that we only want to take into account points that are within some set range of the line that we're going to pick. Okay, so this is a very good method as long as you know which points apply to which line. Now, if you don't, again, we have that problem, and we'll be coming back to later one of the solutions to that particular problem if you don't. But if you do, this is a really, really good solution, and there are lots of efficient mechanisms for doing it. So a lot of people have done work on this. This is the very basic version of the algorithm. And of course, once again, this doesn't just have to be used for lines. It can be used for any parametric mathematical model. Now, when I use that term parametric model, what I'm referring to is a mathematical model that we can define with a few parameters, such as m and c, or x and y, or whatever it might be, whatever parameters that we can put in there. That's what we mean by a parametric model. So we're talking about a few small parameters, as opposed to something like, you know, where you just use vast amounts of data, like in finite element analysis or some of those sort of things, which would not be parametric. So Niall is asking, is this used as the basis for CAD systems? So yeah, for a lot of CAD systems that would use vector graphics and so on, they would use that sort of thing. I think if that's what you're asking me there, where in other words, that they use a mathematical model for the different lines and so on. If you then want to try and put some form of render onto it, that's a little bit different. And if you've got some measuring system for, as I say, you know, something like finite element analysis or that, where you're going to look at very dense data, that's a different matter. They're generally not parametric models. But where we're dealing with a mathematical parametric model, any of these systems can be used. So it's not just for lines. It's just that a line is the simplest one that we all understand and we can kind of do on paper quite easily. So this stands for random assignment and consensus, and that's actually a very good description of what happens here. We randomly assign just two of the points, and we say, okay, now we've got a perfect constraint. We've got 2 points, so we've 2 equations and we've 2 unknowns. Let's calculate the line that passes through those 2 points. And from that, what we'll do is we'll then look at all the other points, and we'll say which of those other points fall within a particular range that we have set of closeness to that line. And we count those up, and we count those as votes. So if we get a particular 2 points, we draw a line between them. We count how many have a consensus with that line. In other words, are fairly close to it within a certain bounds, and we kind of keep this voting register, and we run this a certain number of times. And again, that's a parameter that the user will have to determine based on the system. And when they do that, they then pick the line that got the most votes as being the correct line to fit those points. And this way, Outliers actually have no effect because they don't get a vote for a line if they're a long way out from the rest of them. Okay, and if the outlier happens to be one of the points that we pick in the beginning, then it'll tend to have a line that nobody else really votes for as well, and we have the same effect. So it's quite a clever idea. So the set of things that we do is we randomly just select 2 points to fit a line, which is the exact constraint. Now remember, if it's some parametric model that requires 3 points or 4 points or 5 points, like let's say an ellipse would require 5 points, so then we would need to select 5 points at random, draw an ellipse, and then try and see what other ones fit that. Okay, so it depends on the model you're doing. We're just looking at lines here, but this can be used for many other systems as well. So what we do is as I say, we randomly select 2 points, we fit a line. This is an exact constraint. We solve the model parameters for just these points. We find how many of the other points are consistent with this model. So where consistent means they are within some margin, which we consider an inlier. The number of points is considered the number of votes or a measure of the consensus of this model. And then what we do is we go back to 1 and we take another 2 random points, and we do that a set number of times. And again, that's a kind of like what we call a hyperparameter. It's one of the parameters that we decide as to what we're going to do. So there's 2 kind of, if you like, hyperparameters that we would refer to in this. So what I mean by a hyperparameter is they're not a parameter of the line or anything like that, but they're parameters that we would decide as to what is best for our system. So we will decide what the gap is that we're, what the gap is from our line to the points that we're going to include as having a vote. And that would be one of them. And the second would be how many times we're going to rerun the random algorithm in order to determine what's the best line. And of course, if we don't run it enough, we mightn't find the best line. And if we run it too many times, we waste time. And generally speaking, there's statistical mechanisms that can look into this and say, in the main, how will we do? Okay, so I'm going to do my best to kind of show you this. What I've drawn here is I've drawn a blue line, and this is going to be the line that's going to match onto the points that we're going to pick randomly. And then we can kind of get an idea of the of what values we pick. So let's say, for example, that randomly 2 points have got picked, that one and that one. Okay. Now, I don't do a great job at this because unfortunately, to rotate this, it also tries to resize itself. So I want you to pretend that didn't get resized there, and because it's not really part of the problem that it should get resized. This should always be the same size. It's just I'm trying to work best with the technology that I have. Okay, so let's say that has landed on the point, those 2 points there. We've now fitted a parametric model to that between those 2 points, which is our blue line. We have we can in X and Y, we can see where that blue line is going to cross the Y-axis, for example, and we can determine something about the slope. And we can also count how many inliers we have, and we can see there that in terms of inliers, we have we've obviously the 2 points that are on it, so everything's going to get 2 votes for starters. Then we've a third, a fourth, a fifth, and are we including this one or not? Let's include it for the crack. But again, this is going to be determined much more mathematically, where we've a very definite it's either on the line or it's not. Okay, so we've got 6 votes there, as you can see, for that particular example. Okay. What I'll do is I'll move that over there and we'll pick 2 more points. So let's say, for example, I pick that point and that point, and I think as you see, this one's going to do pretty well. So once again, do my resize here and pretend that I didn't resize it at all. And go right to the limits here. Okay, and let's count how well we've done. So we've got the 2 that are on it. We've got a third, fourth, fifth, sixth. Am I including him? We'll go on ahead 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's quite a lot of points there. That's got a lot of votes for that line. That's a pretty good line, as you can see. Okay. Now let's take an example of what happens when we get a line like this. Let's say we pick that point and that point, which could of course happen. Sorry. Okay, so let's have a look at this. Let's count them. We've got those 2, 3, 4, 5, 6. I'm going to count those 7 and 8 as well. So that's got quite a lot of points, but not nearly as many as the last one that went fully through the system. Okay, so you can see that what we do as we go through each one of these is that it's going to pick up on the ones that are the best. And all we really need to do after we run this maybe 7 or 8 times is see, well, which one has got the top number of votes, and therefore that's our line. And of the 3 that we picked there, we can see that the second one or the middle one is the one that we're likely to do. Has everyone followed the general concept there? Because I think at first when you just see it written, it's not great, but at least if you can see it kind of diagrammatically, you've followed it there, okay? And you can see how you could do this with something like, you know, if you had an ellipse there, and what you did was you took a kind of an inner ellipse and an outer ellipse, and you could start seeing did your points match each one of those and so on as well. So it wouldn't really matter what the specific shape was. We just go via the same system. The problem here, once again, just like the other one, is we don't know what points are part of what line, and that can be a bit of a problem. Okay, so if we're picking up points in an image, it can be difficult to find the one that it suits. Okay, so that's the RANSAC algorithm, and it feels almost strange that's all we're really saying about it because it's such an important algorithm. We may come back to it at different times throughout the semester, but that is the basic idea, and it is actually a relatively simple idea, and it is one that you should be able to kind of be able to say pretty simply. You know, if somebody asks you what's the RANSAC algorithm, it's a fairly easy one to explain. Although you may find that if the other person has never come across it, that it's a hard one to grasp unless you've seen a nice pictorial view of it. Now this brings us on to the Hough transform. Now can I just get an idea, how many people have heard of the Hough transform? And by the way, when I originally did a research master's, I used to call this the Hough transform because it was back in the day before YouTube, and I didn't hear a pronunciation of it. And when I heard somebody else talking about the Hough transform, I didn't know what they were talking about. So this is Hough rather than Hough or otherwise, generally called the Hough transform. So I think we've 1 or 2 people have heard of it, but most not. So this is a very interesting algorithm, and as far as I know, I don't think there was ever a paper published on this. I think this was more of a patent that somebody put out or something like that. It's an unusual one in that way. But it's a very interesting idea once again, and it's all to do with looking at things in a different parameter space than the one that they're in. So if we normally look at things in an XY space, maybe move it to some other parameter space and then try and determine things from there. So it's particularly useful for solving this problem that we have of not knowing what points are associated with what shape. So if we're dealing with lines, what points are associated with what lines, okay? So Hough is useful for more than lines. Any sort of shape that can be defined mathematically or parametrically can be used. And again, I don't cover it here, but I can point you in the direction of some YouTube videos that do it. There's a generalized version that can work for any arbitrary shape. So you can come up with a kind of an arbitrary shape that's going to occur again and again. Maybe it's some manufacturing process and you tend to get this shape showing up quite a lot, but it's not an easy one to describe mathematically. Then you can use a Hough transform on that, and it's very useful for finding these things nearly no matter what scale or otherwise they're at. It'll start to just find them. What you do with them after that then is another matter. Hough works on the concept of changing the space of the parameters, i.e. the values on the axes change. Take the equation of a line as an example. We have y equals mx plus c, and this is where m is the slope and c is the y-intercept, and we consider that in the xy space. But if we rewrite the equation in the MC space, in other words, the slope and intercept space, we get the following. We get C equals minus X times M plus Y. So all we've done is we've manipulated that equation to have C on one side, and the M is instead our variable that we're going to input, and X and Y are set values. Okay. So where minus X is the slope now of this in this new space, and Y is the C intercept in the MC space. So we now have a C as our y-axis and an M as our x-axis, or I should maybe call it horizontal, vertical axis and horizontal axis, because obviously x and y are the other variables. So the point of intersection in the MC space is the slope, and the point of intersection and in the MC space is the slope, and the intercept in the XY space. Okay, so what I've done here now, I want to stress what I've written up here, which is that this is pictorial only. And basically what I've done is I've pretended that I figured out what lines do what, just purely to show you what happens. But these are not the actual lines that would match these points, and I want to make sure that you're very, very clear on that. Okay, so let's say I've got points 1, 2, 3, 4, and 5, and they are points in the XY space. Now what I can do is I can transfer that to the MC space. Each one of these points refers to a full line of possibilities. Okay, so a full line where if I have a particular value of M associated with it, then I will have a different value, a particular value of C. And if I pick a different value of M that nonetheless matches my first point here, I will have a different value of C again. And they will each form a line. And that's what we have here with each of these lines that I've drawn here. And what Hough does is, firstly, it transfers everything from this space over to this space. Okay, and it can do it with the lines here first of all. And what it then does is it does this mechanism where it carves up the MC space it basically into a grid. Okay, so what I'll do is I'll use a very small value of this. So what we do is we carve this up. Now I'm using a very wide spaced grid, but that's fine. And these should be perfectly straight, but they're not. But you'll get the idea. So we've got a grid here that we build. And what we do is, when we've a load of points in our here, what it does is it draws each of those lines in the MC space, and what we do is we just keep a count of which grid got the most crossings. So this grid got one crossing, that grid got one crossing, this one got one crossing, this got only one, this got one, but look at this one, it's got five lines crossing it. So therefore, what we do is we take that piece of information, we say that there, and that there, that value of M and that value of C, we now use those in an XY space, and that should then draw our line back here. Okay? Because we'll have a certain y-intercept, which is given by this value, and we'll have a certain slope n, which is given by that value there, that slope. Okay? So that's the idea of it, and what it does is it literally just counts up the number of crossings that happen in that space. So what are the hyperparameters here again? What are the things that we're going to have to choose? Well, for one thing, we're going to have to choose how big our grid is going to be. Okay? So if we pick a very finely spaced grid, there are some problems associated with that. Firstly, it's going to be more computationally intensive. That's the first thing. Secondly, if there's any, let's say these as you can see with my points 1, 2, 3, 4, 5, they don't perfectly line up. Okay, so because they don't perfectly line up, the lines of intersection of them will not all perfectly intersect. And if you've got a very fine grid, you won't actually find the grid where they all pass through. Instead, what will happen is that will be shared amongst maybe 2 or 3 grids. And at that point, then you're not sure what M and what C to take, and you've got lines all over the place. You're going to end up with far more lines than you really want. If you have a very coarse grid, maybe like I've drawn here, then we're less sure of our M value and our C value, and so we might end up with the line not being perfectly spaced. But the point is that if I have some other set of points here, should maybe use a fatter, some other set of points here, they're going to end up with a load of lines that are in a completely different part of the space, but nonetheless all crossing each other maybe in some place, maybe in this one over here, and they will have a different M and a C associated with them. And therefore, we'd read off 2 very definite M's and C's, and we would draw those points. Now, of course, if you look into this in detail, you can see that my diagrams do not match reality. The M's and the C's that I'm picking here would not seem to match the points that I've picked here. This is just pictorially here, but this is the idea of how it works. So it's quite a clever idea, and there are a number of different spaces that we can move this into. So X and Y can move into M and C, but actually there's another equation for a line that I'm going to show you in a second, and it has a very unusual way of doing it. If we have something that has more than 2 parameters, then we're clearly going to have a 3-dimensional space, and we're going to have to divide that into cubes and so on, so that can be a bit more difficult. But really, in mathematical terms, the algorithm would work the same. Okay? Had you a question there, Niall? Don't be afraid to ask. No. Okay. Okay. Yeah, go on ahead and type there. So Niall has asked what is the main advantage over the previous RANSAC. The main advantage is the idea that we don't need to know what points are assigned to which line. It really doesn't matter. It's going to determine from the number of elements in a crossing whether to decide to have a line there or not, and it'll draw it. So that's the main advantage of it there. I suppose the other question is then, well, why would you not always use the Hough transform? And RANSAC will generally be a little bit more efficient than Hough, and particularly depending on how you implement Hough and so on. Hough can be very thorough, but it might not work for all the certain situations that you want, and it'll be a bit more computationally intensive. Could be a lot more depending on what parameters you choose. Now. This is the basic idea of the Hough algorithm. So I've written here like this. You basically have 2 for loops for each edge or point in X and Y. You do the following: you split the space up into the M minimum up to the M maximum, and you go up by in jumps of M. And what you do is you calculate the line that is associated with that, and then you just move on to the next point. And then what you do is you count up. Find the local maxima in the parameter space as to where they cross. This algorithm can give problems if the line is vertical. Okay, so a vertical line has a tendency to give problems with any of these systems here. The reason being that the m is infinite because it's infinitely up. So there is another version of this that we can use, the polar form of the equation of a line, which is p equals x cos theta plus y sine theta, which is probably a version of the line that you're not as familiar with, but this is basically the idea of how it works. If this is my line, I'll maybe draw my line a different color here, so just have it as different. So the line is the blue one. What we do is we take the line that's perpendicular to that. Can anyone remember the name that I gave a line that's perpendicular to something else, to another line or to a plane? I gave a name to that last week in ASCII. It is indeed, good man Niall, it is indeed the normal. Okay, so normal to it. So, so what we do is we take the line that's normal to that, but that hits the origin, okay? Because there will be other lines that are normal to this, but only one of them will strike through the origin. And what we do is we take our theta value from that, which is what goes into our formula here: x cos theta, y cos theta. Sorry, y sine theta is what I meant to say, and try and think. I've enough feeling I've done the wrong way around. We'll look into that again. I'll let you know if I have. I've feeling the x and the y's. It might just have them the wrong way around. But anyway, it's not too important. Then we take this. Now this I've written it. It looks more like a p, but it's meant to be that that value rho is how it's normally written. That Greek value rho. So that's the length there will determine that. And pretty much any line, you can often look at this situations of this and kind of say, well, there are certain lines that I won't be able to find this for. But in actual fact, pretty much any line you should be able to find the normal that passes through the origin. The only possible one that you mightn't have is where the line itself passes through the origin, in which case the normal is just 0, because it's a 0 distance to it, to the origin, and your angle is just whatever the angle is round to it. So that problem actually gets solved. That's the opposite of the problem that we had previously, where you had an m that was an infinite slope. We can't really deal with infinity, but we can deal with 0. So this is why this version of it is slightly easier. This is basically just the same thing as the same algorithm, except in the theta and rho space. Again, before we do anything, we do need to be careful that we've calculated the theta value correctly, because when you're calculating the theta value, if it is directly straight up, you know, when you're doing that arc tan or inverse tan calculation of the opposite over the adjacent, you can end up with a situation where you're dividing by 0. So you do still need to deal with that problem. That's fine. The other thing to be aware of is we mentioned the canny edge detector the last time, and if we've used canny, then we have a situation whereby we already have calculated the theta, so moving into this version of the algorithm is a little bit nicer. Now, this guy here, Tailsen Kurting, I hope I'm pronouncing him correctly there, he has a really lovely animation of this version of it. And it's if you just click on that and go to 3 minutes 32 into the video, you can also watch his description of it too, which is very good. But that's where the animation starts, 3 minutes and 32 into it. And it's a really nice animation in this version. I tried to draw it, but I didn't do very well because my drawing application here doesn't work very good for me. Firstly, I couldn't draw a very good sine wave for starters, and that's what, or a sinusoid, and that's what we have here. So what I did was I did 5 copies of it. Now the problem is these can change in amplitude, but they don't change in frequency. And unfortunately, when I go to resize one of these, it changes it in every direction. So it just wasn't really working out for me. So you're far better go and look at Tail's animation there. But this is the basic idea. In the rho theta space, what happens is that you have the sinusoidal shapes going through it rather than lines. And again, there will be crossings there, and you will count up, you know, at what point do you get the most crossings. There will be an example. You calculate it down there and across there. Now, of course, you may spot that actually, well, there's another crossing over here, but what you find is that that's exactly the same crossing, just 2 pi later. So you're basically going to take the value that's lowest, because that just basically is a bit like having the line that's gone fully around the circle again and gotten back to the same point. So it'll amount to the same thing anyway. So it's good to have a look at that animation, because the other thing it shows you is that there's quite a bit of calculations go into this thing and how it goes around, and that kind of gives you the idea then straight away that actually this is not going to be a very, very efficient algorithm, even though it might be quite a thorough one. Okay. So again, we'll finish this part of the lecture tonight on this. Some things to consider with Hough. We need to pick our hyperparameters here. So we need to decide what are the increments of theta and what are the increments of rho, or if we're using the MC space, what are the increments of M and what are the increments of C. If we go too large, we cannot distinguish between different lines. They're hard to tell. Too small, noise causes lines to be missed. And we also have a situation where we might have an awful lot of lines in different directions. One thing to be aware of with this, maybe that it's not obvious in your intuition. Let's imagine that we have, sorry, what I'll do is I'll just draw basically an image here, okay? So this is maybe an image box. And let's say, for example, that in this image box, I'll have some lane markings. Sorry, this is going to play poke with me. Okay. And we've got other... Right, ignore those other lines because they're happening just because of the pressure the system has been put under. What is going to happen is that we will, for each of these points here that are the ones on the left that fall on a line, this will calculate a line that goes like that. Okay, and it doesn't know, or it doesn't really take into account with Hough. We just get an M and a C value. It doesn't take account that it ends there and begins here. That's up to us to try and determine later on. So we've really just got one line that goes through it. Same with RANSAC. RANSAC tells us that we've passed through 2 of the points, but it assumes that they continue on for good in and out of the picture in every direction. So again, you may need to do a little bit more in order to determine this. And of course, this thing can quite easily determine that we've got multiple lines. We've got maybe another one there. And now what you've got is you've got a point at infinity. You can kind of see where the road is going to. You've got a number of pieces of information like that. But do remember, they may disappear off into the sky and so on. So it might make sense to take all of that into account. Okay. So I'm going to stop that recording there. At that point, we'll take a few minutes break.